Thank you for the introduction, and it's always feels being back home here at UPenn. Today we'll mainly introduce our work on learning and control for safety, efficiency, and the resiliency of embodied AI. Everything here is completely different from my PhD thesis defense. So nowadays, with the growing of the full dynamics model of the entire system, and hopefully in the future that in robotics fields, in applications like autonomous driving, drones, and manufacturing, mobile warehouse, we will also have better systems with all these learning-based methods. And especially in my research, I've been focusing on multi-agent learning and control. Because we do see the trend, say, in the future, in scenarios like manufacturing places, mobile warehouse, autonomous vehicles on streets, there will be many robots in the same environment. So we have to consider the interactions between these agents and also with the environment. And with this kind of trend, it is important to solve multi-agent learning and control challenges in the future. So however, we are still a little bit far away from that stage. So if we just play a video game and train some reinforcement learning in StarCraft, and we lose or we die, it's okay, just a restart. But if it's a real robot, then the cost can be pretty high. And cases like autonomous driving, it can be even dangerous to human life. So we have to consider safety requirements for the safety critical systems. And meanwhile, when considering all these requirements in a multi-agent environment, efficiency is also another challenge we want to solve. That if these agents do not really coordinate very well, it can be cases, say, the entire system is just a chaos, so it's not functioning very well. So safety, efficiency, these are all challenges we want to solve. In terms of these motivations and problems we care about, in today's talk, we will mainly focus on learning and control with communication capability among agents. If time permits, I will only have one slide introduction for data-driven robust optimization and the several physical system security. So first, basically, learning and control with communication capability. This is my career work, and we have been focusing on this topic in recent years in our group. So thinking about systems like multiple autonomous vehicles on streets, nowadays these vehicles are embedded with communication capabilities. There can be both vehicle to vehicle and also vehicle to infrastructure communications. And then the opportunities here is we do see ubiquitous sensors and actuators, and basically we can consider this as a data-rich environment. And we can have faster communication and computation capabilities for these systems. But meanwhile, we also see a lot of challenges here. So first of all, this is some complex dynamic system that from every single agent's perspective, we cannot just assume we know the full dynamic of the entire system. And also we want to consider a lot of these learning algorithms, it's hard to say we have 100% accurate results. So we have to consider all these like learning-based methods, uncertainties, and if we feed this to the decision-making process of the system, how we can deal with these uncertainties. And of course, as we mentioned, these are safety critical systems. We want to define the safety requirements and make sure through this learning-based process, these requirements are integrated in the algorithm. And usually these are large-scale systems that we want to have some distributed decision-making mechanism instead of, say, one centralized planner or controller make decisions for all. And finally, we want to quantify the benefit of communication and really understand the tridirectional relationship among communication, learning, and control. So in the following slides, we will mainly use this kind of loop of learning and control to explain our research contributions. So the first part, we will introduce uncertainty quantification for collaborative perception. And then we will talk about our design of safe and scalable multi-agent reinforcement learning algorithm with communication capability among agents. And then we will define benefits of communication and reward reallocation scheme to incentive agents to communicate and coordinate with each other. And finally, we will introduce our recent work on robust multi-agent reinforcement learning and the state uncertainties, both from a theoretical proof analysis perspective and also algorithm data. So first is about answering quantification of collaborative perception. I think we can use these figures to show the motivation of caring about uncertainty quantification from maybe control background perspective. So, for example, if we have some object detection result based on a deep neural network and tells us, say, okay, the prediction of the object position is at the red box, but the ground truth is actually the green box. If we just directly use red box for path planning, then it's possible, say, we go to an unsafe path. But meanwhile, say, instead of requiring the object detection part to be 100% accurate, we have an uncertainty computation shown as the orange ellipsoid. Say, I know my model is not 100% accurate, but here I can define, for example, this is my uncertainty about the locations of these 4 vertices. And later we can use this gray box as our prediction about this object positions. And then we can say, okay, now I'm just using this gray box to do path planning and control, and we can have better safety guarantees. So,
what's this? This is with cameras? Or?
Yeah. So for the first step of our work, we using this collaborative perception based on LiDAR point cloud data as a starting point. So in recent years, in computer vision society, collaborative perception has also been a hot idea. Say, okay, control and decision-making part, we have this multi-agent coordination idea for decades. But in perception side, it's like if we have some sort of sharing among agents, people want to show, okay, things can actually improve object detection accuracy. And there have been different methods like sharing all the raw point cloud data, or say only sharing some intermediate features. After every agent first process the raw data through several layers of a neural network, and researchers have designed different neural network structures and different algorithms to show, okay, this sort of sharing information can improve object detection accuracy. And meanwhile, uncertainty quantification, for example, like a conformal prediction, these sort of ideas have been very hot, and it seems like we are now in a stage, say, okay, we want to really understand the uncertainty of the prediction result from the modeling part. And there have also been methods like Monte Carlo dropout, DP examples, and try to, for example, average the result of several models. But these methods are usually too computationally expensive. Even in inference stage, you need to calculate the results from several models. So not really directly apply to tasks like autonomous driving that we need this sort of, for example, 20 frames for detection in every second. There have also been methods like direct modeling, which say using the neural network to predict the uncertainty together, for example, predict the covariance matrix together with the mean value. And usually this kind of direct modeling method is over-optimistic. So it's like even the model is not accurate, still the uncertainty is very small, so over-optimistic. And compared with conformal prediction, later I will show that actually our method, specifically considering reduce the uncertainty of the prediction result even through the training stage, while conformal prediction usually is after the model is trained and just quantify the uncertainty. So our method do uncertainty reduction and uncertainty quantification. And we can basically calculate the uncertainty of our model just through one inference pass after we have calibrated uncertainty result through the training process. And we will show that our method can reduce the uncertainty and also improve the accuracy for object detection tasks. Methodology-wise, the key component includes 2 steps. So first step is we do, inspired by the idea of direct modeling that because object detection can have different structures of a neural network, we do want our framework to be compatible to like different designs. So we don't really like change the structure of the model, not necessary. Instead, we only add several additional layers in the final part of the model, and also add additional output, for example, covariance matrix of the position of the vertex as an output we want to learn through the training process. And we define the loss function as a tail divergence loss part. Say we specifically put like reduce the volume of the covariance matrix through this training process. Basically, through this kind of loss function design and this additional like output through neural network, we can learn, or we can predict the mean value and the covariance matrix together. Meanwhile, as we already mentioned, direct modeling itself can be over-optimistic. So through the training process, we also have a calibration process. So our first step trial is based on also a classical statistics method, bootstrap. So the process is we partition the data set and doing this retrain and the calibration, for example, 100 times of train on different folds of a sub data set through the training process. And every time for the validation, we can also calculate the average neural network prediction error. And we add that part of like a calibrated uncertainty together with what is direct learned by the neural network. And this way, during the inference stage, basically the uncertainty represented by covariance matrix of positions of each vertex is calculated as what the neural network result give us, plus the calibrated part through this retrain resample and validation. So this is the methodology part. What we will get through inference stage will be like these videos. So without uncertainty computation, basically our detection is like 20 frames of images, like these are point cloud data images in 1 second. And basically it shows the bounding box as one object detection. With our uncertainty computation method, we also get these orange ellipsoid at the vertices of each bounding box. So this shows our uncertainty result about the positions of each vertices. And we can do uncertainty computation for different collaborative perception methods. So for example, the left video is some method called the disconnect. It basically shares intermediate features for neural network among neighbor agents. And the right video is a method called upper bound. So it shares all the raw point cloud data among agents. And here we also compare, say, sharing intermediate feature on the left part with, say, not sharing. Every agent just do its own object detection. And we compare the uncertainties through the inference stage. Basically, if they see like a larger orange ellipsoid, it means the uncertainty is larger in general. We also have these table results to show, okay, what are these evaluation matrix data on a shared open source data set. So here we have two tables. The first table mainly compare accuracy evaluation, because before we really train our model and do all these evaluation, we are concerned to say, what if we care about reducing uncertainty that also reduce the accuracy? Then it will be like a trade-off between these metrics, and then we have to consider which one is important exactly. And later, after we doing this evaluation process, so here basically every row is one different uncertainty quantification method, and the final row is our method, and the previous row that's some baseline we compare with, and every column is one collaborative perception method, and this lower bound is like a not doing collaboration on the perception part. Agents just do its own object detection. And basically this accuracy number is the larger, the better. And we can see that for collaborative perception, with our method, say specifically including reducing uncertainty as the objective part, then we can actually improve accuracy for this collaborative perception part. So which is good, means these two, accuracy and uncertainty, they don't need to be like trade-off metrics. We also compare the uncertainty evaluation. So NLL is a negative log likelihood. It's often used for basically comparing model prediction uncertainties in different machine learning tasks. So here we can see that with our method, we basically reduce uncertainties up to 4 times compared with other baseline uncertainty computation methods. So this means by designing the uncertainty reduction and uncertainty computation algorithm very well, we can do, say, both improving the accuracy and also reducing the uncertainty. And another insight here is usually computer vision tasks don't include uncertainty quantification as one matrix, but later we think UQ can be another metric to evaluate, for example, under different scenarios, what kind of information we should share together with the accuracy metric. So, for example, if we compare this middle column sharing only intermediate feature and the right column of sharing all the raw point cloud data, though sharing all the raw data has the best accuracy result, but in terms of uncertainty of the model, sharing intermediate features is better. And of course, we have to consider, for example, limitations as what is the communication bandwidth, etc. But previously, people think about, okay, to really improve the accuracy, it's worth to like invest on this communication cost part. But if we think about uncertainty communication as another metric, then we actually have another motivation of say, okay, maybe sharing intermediate feature is better than like having this large communication cost of sharing all the raw point cloud.
Maybe you could say, can you tell us a little bit about the communication cost of these approaches?
Yeah, there are some survey papers in, for example, Mobile Computing Society comparing, say, sharing like a different size of sensing data, what will be the communication cost and what will be the communication delay, etc. For these, for example, baselines of collaborative perception methods we use, most of them do not consider, for example, communication delay yet. But there are indeed many design about saying, okay, even sharing intermediate feature, not just sharing the impaired feature metrics, instead only sharing those that are important. So in collaborative perception society, there has been like a lot of effort on reducing the communication cost to make this methods really practical in the future. Yeah, so our method here is to show, okay, so different kinds of maybe neural network structure design you have here by including this uncertainty reduction and uncertainty quantification in the methodology, then it can like further improve performance of these methods. Yeah. Other questions?
Is there a sense of like overconfidence by reducing your uncertainty of these objects? Maybe like you're arbitrarily like you might be like reducing your uncertainty, but your actual solution is not super accurate too, or does it come hand in hand?
Sure. So that's why here we have, when doing this evaluation of uncertainties, so first of all, you separate the training validation data set with the testing data set. And also our metrics is considered as one, like a fair comparison, a good metric to evaluate how good your model is providing this uncertainty result. So in the metric itself, it includes like if your prediction accuracy is not good enough, then the uncertainty should be larger than NLL is small. It doesn't mean say covariance matrix volume is small, NLL is small. It's not like that. Okay. Yeah. And we also have some recent publication about, say, okay, after the object detection side, we have a certain quantification and how we can propagate this part of the information and knowledge to the downstream object tracking tasks. And these methods specifically work well and improve performance significantly in cases with high occurrence. So traditionally, object tracking will perform bad if, say, some object is seen in frames, in maybe T, but not seen in T+1, etc. So with occurrence, then it would be harder to really do this identification matching among different frames. But if we consider ascertain quantification through this object detection part, say even object detection part is not that accurate, still through this tracking stage, through this object ID matching algorithms, we have some hope to improve the tracking result. So here we want to show, okay, so even within this different modules of computer vision tasks, we propagate the uncertain information that can help a lot.
Is your method specifically for point cloud perception, or can it be used for other modalities?
So for now, we didn't specifically, so our work, we didn't specifically run experiments with camera data yet. So we start from point clouds purely because open data set wise, it's easier to find the literature and to compare with. There are also example other groups working on uncertain computation using image, RGB, that sort of data. So I think methodology-wise, it just shares a lot of common parts. So for example, having some statistics-based methods to calibrate your uncertainty results, etc. So yeah, but of course, say there will be a lot of design detail if you have maybe different data type, etc. So that's why I think uncertainty quantification is just started, so it should be continue to be a hot research topic in the future. Yeah. And now we would like to introduce our work on safe and efficient multi-agent reinforcement learning. And specifically, the scenario we consider using this Connecticut autonomous vehicle scenario as an example, say these are autonomous vehicles and every agent will make their decentralized or distributed decision. And from every agent's perspective, we do not have the exact state transition module if we're considering the states of all the other agents in the system. So that's why it's relatively, say, model-free setting, considering how agents interact with each other and how every agent interacts with maybe in the environment. It can be mixed traffic, there can be human drivers, etc. We don't assume we know their dynamic model. We can only have our own observation, computer vision part, and then we need to decide how to react. So it's relatively model-free setting. So that's why we go to this multi-agent reinforcement learning approach instead of traditional model-based control approach. And meanwhile, every agent does have some knowledge, for example, for its own continuous control dynamics, like to do this changing lane, keeping lane maneuver, how to what should be the throttle, steering angle, etc. So we assume every single agent that has some model-based knowledge for itself. And then the decision-making process will include, say, we put some discrete action, strategic level of action, at every time step. Agent I needs to decide, should I keep lane or changing lane with a very fast speed, or keeping lane but slow down a little bit, etc. For this kind of discrete action on this multi-agent reinforcement learning side. And meanwhile, we also need to make sure, say, okay, what is explored by this learning part, really there exists safe controller to finish this changing lane maneuver instead of say, oh, changing lane, but hit on some other vehicles. So we really need to consider, okay, what should be this sort of integration from this learning side and control-based side of this. Some background knowledge about multi-agent reinforcement learning. So similar to reinforcement learning, agent can have its state information and it can explore some actions within its own action space. and it will get some reward feedback from the environment part. But the main difficult part of MARL is the reward of every single agent will also be affected by the other agents in the environment. So for example, the reward will be related to the joint state and actions of all the agents in the environment. So this makes it challenging for every agent to really make a decision, say what policy to, what action to take at a different state, because it needs to understand what is interaction within this entire system, how will other agents affect its own reward, etc. So to solve these challenges, basically the problem we have here is we want to design some distributed or decentralized policy learning methods for every single agent. And the agent wants to, for example, maximize accumulated, it can be discounted reward. And meanwhile, here we assume this is an unknown global state transition function here. And researchers have been designing a lot of algorithms to solve this kind of a challenge. And some popular framework is like a centralized training and decentralized execution. So basically through the training stage, every agent can train like a Q function related to the large joint state and action of all the other agents. But in execution stage, basically the policy is only say selecting its own action at this moment. So this method has been very popular, but it really does not scale very well when they have a large number of agents, because during the training stage, there will still be this very large Q function to learn. And there have been other efforts, such as training a purely localized policy, say only based on local state instead of, for example, joint global state. But this kind of method lose too much information from what other agents interact with each single agent value. And there have also been methods from the distributed optimization perspective, say design the purely decentralized MARL algorithm. But still, during this training process of the algorithm, every single agent will need to get a copy of the parameters from all the other agents. Actually, the communication cost through the training process is pretty high. So then our question is, okay, so what should be a better way to design scalable MARL algorithm, considering, say, agents can have communication? And meanwhile, we also need to consider these safety requirements through this MARL interactions. So there have been a lot of work on this single agent SafeRL, but most of the approaches cannot directly generalize to what happened in MARL setting, because the definitions of safety requirements and the definitions of objective reward setting can be quite different in MARL case. And we need to have a better design considering both, for example, the objective of finishing task efficiently and meanwhile satisfying safety guarantee. So in this research line, our main contribution includes two parts. So first, we designed a computation-based truncated Q function method for scalable MARL algorithm. So the main idea here is this is an actor-critic algorithm that every agent learns its own, for example, actor function. Basically, we assume this can be neural network approximated, and the actor function will decide, for example, the action to take. Given here, the state part is we define it as a truncated state. So the meaning is we assume every agent I can communicate with its NK neighbors. And basically, the state and action information for learning a Q function will only be related to these NK neighbors instead of assuming like a large-scale global joint state and actions through training. And meanwhile, during execution, so we assume on streets, the vehicles can still have this kind of sharing information capability. So it's also, say, based on this neighbors state information instead of saying, okay, every agent just naturally has a global state information.
Can you tell us a bit about the constants on the right? on the right side of the inequality.
Yeah. So the assumption here is for showing what kind of error bound we can have, we assume, say, okay, during the training stage, basically these NK neighbors communicate are fixed. So it's not in like a mobile setting yet. And then we analyze, say, okay, so the error between this truncated Q function and a Q function, say, in the centralized training setting with global joint state and action can be upper bounded. And the bound is related to R bar is the upper bound of reward function of agent I. So for example, agent can have different reward in different state. And gamma is the discounting factor of this value function. K is basically it's actually this is kappa. So here is we assume NK means like agents communicate with like a key hop neighbors. Yeah. So basically here is if the agents are communicating with maybe many hops of neighbors, it's very close to say, okay, agents basically get to the global state. So the error is getting very small. So yeah. Other questions? So this is the first part about utilizing communication capability and the design of scalable algorithm. So of course, in experiment, we are not like just fixing the number of agents communicating, the vehicles are moving, so later we will show. And also the good part of this algorithm is it's not affected by the total number of agents in the entire team. There can be 100 vehicles, but every agent I only cares about maybe like the 5 closest agents within this communication range. And it can learn something instead of saying, okay, I can only learn with all these global states. And in terms of the safety part, we designed a module called safe action mapping. So the idea is very similar to safe action safety filter, for example. So basically, we will, for example, of course, we want to define safety requirements like no collisions among agents and no collision among agents to the environmental obstacles. And basically, every actions explored through the training process by the RL will be first checked by this safety requirements. So if this action is safe, then we don't change it at all, just directly put it in the replay buffer for training the MARL process. If the action is not safe, then basically we will just filter it out and check in another action. So we will only save these safe actions in the replay buffer for MARL. So this way, basically through the training process, the agent gets some ideas, see, okay, at this moment, at this stage, whether it's safe for me to take some action AI. And every agent do its own safety checking. So using its own, for example, physical dynamic knowledge about its like position, velocities, and also using its own knowledge about surrounding vehicles, no matter it's other agents or human-driven vehicles. So basically, if our requirements is about no collision and every agent maintains this no collision requirement, then of course the entire system no collision. And this is how we integrate the safety requirements with this MARL learning process. And basically, the MARL reward only cares about all these efficiency related objectives, like what we show in these experiments. So we simulate different numbers of autonomous vehicles in this color simulator and compares the vehicles trained with MARL algorithm with the safety shield and without the safety shield, and basically with the safety module part, the cars learn driving smoothly in different settings, different maps, and of course we can also change the number of the agents in the environment, and we can see that these vehicles basically can drive smoothly. Of course here, so it's just a normal environment setting. Later, I will also show like a challenging scenarios. So we also compare, see, okay, what if it makes the traffic environment, the red vehicles are trained by our algorithm, and the blue vehicles are basically just randomly generated, controlled by color. So we don't program this algorithm, and see whether these autonomous vehicles can react smoothly to different behaviors from the blue vehicles. And we also want to use this obstacle at corner scenario to show when communication helps a lot in these scenarios, like originally without any communication. So the vehicles, it's hard to see there's some traffic jam until they reach the corner, and then it's really like a late to change lane. So that's how a traffic jam forms. And later we show, for example, they have information sharing, like every vehicle share their velocity information with the neighboring autonomous vehicles. Then this red vehicle learns, okay, the leftmost lane average speed is changing very slow, and it's better to change into a faster lane even before it reaches the car. So, and we also have this kind of table to compare our method with baseline method. Say it has the global state information through training. Basically, we want to show, okay, performance not dropping significantly, and we show like a different percentage of autonomous vehicles and human driving vehicles here. I want to mention here that we actually put the same safe action mapping to this baseline algorithm with the global joint state information. So that definitely helps the algorithm to get like a higher reward function, but the original baseline does not have any design about the safety part at all. And here in experiment to make sure this is a realistic algorithm, the state information, it is continuous state, but it's relatively low dimensional state. We are not using, for example, just the raw image as the input for the RL part. It's just like position, velocity, and say object detection result from the computer vision part. And for actions, we use discrete action, like a keeping lane, a change left, or change right. And for the reward setting here in the video, we show basically we set up identical reward function for all the agents. They want to improve average velocity and comfort of the entire system. And some detail on this, like safety checking, we have been using for this specific experiment. For example, we have different, we basically rely on the theory of control barrier function, and by solving CPS QT problem to find out whether there exists like a feasible maneuver to doing this changing lane and keeping lane actions at different stage. And we define barrier functions for lane keeping action as, say, maintain a safety distance with the front vehicle. And we define barrier function for lane changing maneuver as they keep safety distance with front vehicle in the current lane, and also for the lane I want to change with the front vehicle to keep the safety distance. So with this kind of safety action matching module, we can show that basically our method can make sure the vehicles maintain a safe headway with the neighboring vehicles, where the baselines, like as shown in these black figures, cannot. And we also compare like the number of unsafe actions avoided through the training process and the different traffic density. And here we want to compare, say, just the MARL algorithm without any safe action module compared with our algorithm with RL caring about improving efficiency, and meanwhile safe action mapping module kind of filter out unsafe actions. So we can check the cumulative reward part, and basically here we want to show considering safe actions, it helps in these kind of physical dynamic systems through the training process that we can only execute safe actions instead of like just a randomly explore, because when there is some accident happens, some collision happens, this episode have to stop and then restart. So kind of interrupt the learning process of like learn a good policy to improve the reward. So from this perspective, safety also helps improving the reward through this MARL learning process.
Do you do any experiments with the train safe MARL without the safety barrier function afterwards? Like, so like, because
oh, so you mean after training, whether the barrier is still there or not? So for the results shown here, so after training, the safe action module is still there. So I think there is currently, say, this is also a kind of framework, say, even after training, the safety shield is still there for most like safety critical systems. This is still the framework that people will kind of rely on. Yeah.
I mean, but then like, what's the point of learning the RL system if you have this like nice control barrier function that's always on it?
Yeah, as we mentioned here, the control barrier function, the dynamic knowledge is only about each individual vehicle's like dynamics, but it is no idea, say, what the other vehicles will do in the environment. What about like all these mixed traffic human driving vehicles? So in terms of this kind of this multi-agent perspective, how to interact with the other agents, how to interact with the environment, that part is learned by MARL. Yeah.
But you don't have any notion of like the underlying RL policy having actual safe maneuvers now, because you always have the safety barrier function on top of it.
So the RL part action definition is different from like what control barrier functions do. RL parts action is more on this discrete action side, and well, control barrier function learns, for example, circle, steering angle, this sort of control values. So they are actually learning different things.
The low level function.
Yeah, doing different decision making part.
Okay.
There have also been methods like, say, okay, the RL part and the control part, basically they have the same action space is the control input space. So then there can be different design. But I would say for multi-agent setting, that might not really apply because your action space will explode if you have many agents. Sure. So that's why here we have this kind of separate design. Yeah. And when we talk about safety, actually how challenged we put the environment matters a lot. So for example, if all these human drivers behave normally, that's fine. What if there's somebody running the red, or say somebody suddenly brake on the highway? It will be kind of very difficult for the current technology of autonomous vehicles. And our problem here is assume these green autonomous vehicles, they can communicate with each other, for example, they can share their detection about the surrounding vehicle position velocity with the other agents. Can they design better MARL algorithm to improve the safety and the efficiency of the system, even under these very challenging scenarios? So our main design here on the computation here includes two parts. So first, at this time, we're considering kind of abnormal behavior from the environmental vehicle side. We need a stronger safety shield, a more challenging, more complicated barrier function design. So instead of just using like a linear barrier function, in here we are using a second order style of barrier function. Say, if the ego vehicle wants to maintain safety distance with the surrounding vehicles, basically it will use square of the velocity information to design this barrier function, and then by solving this QT to check whether at this moment there exists a feasible control input to do this changing lane maneuver. So this is kind of an implicit way of considering, okay, there can be a large change of this acceleration part. So to describe our safety shield considering abnormal behaviors. And we also need better neural network through the learning process for MARL. So here, basically, we design a GCN transformer structure on this MARL part to use this as the representation of the dynamic of the surrounding environment for the actor neural network and the critic neural network. So this way, the agent understands, okay, through this different time steps, what is positions and relative positions of the surrounding vehicles with every ego vehicle, and figure out, okay, maybe some objects is really moving very fast compared to the others, and should pay attention to this kind of object. So through these two main contributions, we can show that here, based on our method, we can significantly improve safety rate even when there is like some abnormal behavior right in the red vehicles. So here, collision-free means no collision between these learning agent CVs to the environment human driving vehicles, and also no collisions within the system. So basically, it's accident-free. And as long as there is any collision, no matter it's with the surrounding environment vehicle or with the other agents, it's counted as like an accident scenario. So we compare, say, baseline like neural network part the same, but just not using this safe module safe action checking. What will happen? So significantly, we can improve the safety rate, and we also compare, for example, under this suddenly park on highway scenario. Again, we can improve the safety rate, and the table shows every part of the same, just a different neural network structure. Compared fully connected neural network structure with our design adjacent transformer-based structure. And again, neural network structure design also helps improve both safety rate and efficiency of the neural network. And we also test our algorithm, our learned policy. Basically, all these testing shown here, they are just the same neural network policy. They are not like changing neural network specifically trained for just the individual scenario. So it's the same policy function. And also we put it in like different testing scenarios, like changing the number of agents in the environment. And of course, the behavior is different. And we can show, okay, our method basically can improve safety rate and efficiency. Also, we compare, say, okay, what if the agents, they don't communicate with each other and not coordinating? So basically, even we keep barrier function, the same neural network structure, the same, but without this kind of shared information, we lose safety rates. And with our neural network trend, considering these challenging scenario, we also show, okay, if we don't put it in a very like a difficult testing case, just say a surrounding environment vehicle drives smoothly, we can indeed have 100% safety guarantee. So when we talk about safety, it's actually very relevant to the testing case, whether it's very challenging or it's kind of just a normal scenario.
So the second one has the barrier functions still.
Yes, but just like no shared like information
No
about CVs. Yeah.
And so what would happen if so that second case is closer to like if you just had like a random policy. Like if you had a random policy and you had the safety barrier function around it. Like
it's not a random policy, still we train.
Yeah, it's still trained, yeah, I agree.
Yeah.
But like what would happen to the car if you had just a random policy underneath?
So mostly we will see maybe the vehicle who is very close to this bad behavior vehicle is okay. It can be detected, but for following vehicles, it's not easily to detect abnormal behavior and does not really have enough time to react. So yeah. Okay. So previous scenario, we just assume agents would like to communicate and coordinate with each other. But what if optimizing some system level objective will sacrifice its individual benefit, right? So, for example, if we have D yield to C, to let C finish changing the maneuver, okay, so system-wise efficiency is good, but D kinds of slow down. So the question is, how can we design incentive mechanism to motivate agents to communicate and cooperate with each other? And our proposed methodology here is Shapley value-based reward reallocation for MARL. Say, usually the critic function is defined as a Q function through this critic algorithm. But here we define the critic function according to each agent's contribution to the improvement of the entire system's value. And basically, the agents can get a reward proportional to its contribution. And Shapley value has been a concept in cooperative game, but previously it's been mainly in static game. And recent years, it has been applied to quantify the value of specific data or feature to supervise the learning models. And here we basically define Shapley value for MARL setting. And we prove that this is efficient reward reallocation because the system's reward will be completely distributed to each agent for cooperative policy learning. And we can also prove this is stable reward reallocation if the value function satisfies convex game condition that all agents will stay within the position, communicate, and cooperative to optimize the objective. And we also compare our Shapley value critic algorithm with, say, several common settings baselines in MARL, say, assuming every agent has identical reward function that is cooperation. And we can show basically we can train better policies to improve the system reward because if the agent really contributes more to the system, it kind of gets the benefit as like an incentive. And the last part, as we introduced from the beginning, say we have what actually computer vision part is not perfect, and we can have methods to quantify the uncertainty about object detection, about tracking, about trajectory prediction, etc. And we want to analyze in a multi-agent setting, what if the state information has error, what agents will do, right? So definitely the policy will be affected. So I think we are the first group to work on state perturbation for multi-agent setting. And previously there have been work on, for example, state perturbation for single agent setting, but that doesn't have this kind of interaction of agents, Nash equilibrium, this sort of flavor in single agent setting. And there have also been a lot of attention on transition kernel uncertainty for considering RL because this kind of mapping the simulation to reality gap problems. And our analysis is beyond that, we also need to care about state uncertainty, especially when, for example, state information comes from all these computer vision part knowledge. And our contribution here is first, mainly theoretical wise, we define this problem as system agents basically compete with adversarial agents, while the adversarial agents' objective is perturbing the state information to minimize the system agent's reward. And we first define equilibrium concept in this setting as robust equilibrium. So it has the Nash equilibrium setting, say if only one single agent I deviate from this robust equilibrium solution itself cannot really gains more reward or total value function compared with its stay within this robust equilibrium policy. So basically this is a Nash equilibrium flavor, but the key difference here is system agents only has perturbed the state information instead of true state information, but adversarial agent has the true state information. And we can prove that under very special scenario, this robust equilibrium exists in tabular case, basically finite state, finite action setting, bounded reward. And the condition is when adversarial perturb the state according to some bijection function, the robust equilibrium exists. So it's kind of very special setting. First step of theoretical analysis, and all these full proof detail we can check in our paper. However, in reality, we actually don't have much knowledge on this adversarial side. So basically, when robust equilibrium does not exist, the best agent can do back to this kind of robust policy scenario. Basically, it can maximize worst case expected value under state perturbations. And again, we have all these proof detail about this kind of robust agent policy actually exists. We don't need to have specific assumptions about adversarial policy of adversarial actions at this setting. And in algorithm, we can show that by considering potential state error, state perturbations through the training stage, we can indeed improve mean episode reward compared with several baselines. In this sort of like a MTE is kind of very basic setting benchmark for MARL algorithm evaluation. And very recently, we also push forward these algorithm design to physical dynamic system setting, as we show that when state information has error, then of course these vehicles easily have accidents. And our design is including two parts. So first part is on the MARL algorithm side, we're considering robust MARL. Basically, it's through what we call a worst case Q function design. Basically, for the Q function, we are solving like some maximum problem instead of only like maximizing the Q function through this training process. And for safety shield part, we also expand robust CPS, robust variable function, assuming that the system state information can have error. But of course, through the training stage, we have no idea what kind of perturbation will really happen during the testing stage. And we compare our method with baselines like using some safety shield, but not robust safety shield, and we can show it can improve safety rate significantly. But I think these are still just a very early stage research topic. There will be a lot of space for this kind of safe and robust MAR algorithm design in the future. For test bed way, we basically have this advanced vehicle, which has maintained this kind of research community effort for many years. And we also have, for example, very first stage trial of two vehicles communicate and coordinate to avoid obstacles, etc. Basically, we have shown that considering communication for the learning and control process, we can indeed improve the system's performance through computer vision process. For example, collaborative perception can improve the accuracy and of the detection result. And meanwhile, we can design uncertainty reduction, uncertainty quantification method to reduce the uncertainties of the prediction result. And in the future, we believe that uncertainty quantification can also inspire communication using uncertainty as an additional metric. Together with accuracy, we can decide which kind of information is valuable in different scenarios. And communication also helps to improve both safety and efficiency in multi-agent reinforcement learning in like normal scenarios or very challenging scenarios. So in the future, we hope uncertainty quantification can bridge the gap between the perception computer vision side to the planning and control side for multi-agent systems. And we will continue to work more on safe and robust multi-agent reinforcement learning in the future. And in terms of other topics, during my PhD, I've been working a lot on this data-driven robust optimization. Recently we have also designed like a robust MARL version of this kind of vehicle scheduling algorithm in mobility on demand service. We need to schedule both like charging process algorithm and also passenger pickup algorithm if these services are provided by needs. And it turns out that robust MARL is better because it doesn't need to have restrictions about objective function or constraint function must satisfy some specific format, then this robust optimization problem is solvable, etc. So it's more flexible in designing all these objectives and constraints to satisfy through this algorithm training process. And we have also been working on several physical system security. And during my PhD, I have mainly been working on theoretical analysis like game theory, setting for several physical system under attacks, coding scheme for stealth data injection attack detection. And recently, we have also been working on, for example, deep reinforcement learning for power systems, and also like a game theoretical quantum key distribution framework. So we believe that in the future, multi-agent reinforcement learning can also be helpful for several physical systems considering these potential cybersecurity risks. And here on my team, some students already graduated. And we also have undergraduate researchers in our team. I think in the future, we will continue to work on both theoretical part of MARL and also practical algorithm design part, and implement and testify the algorithm on real robot systems. And we really hope to improve safety, efficiency, and resiliency of the future embodied AI systems by integrating the learning-based method and control-based method. Yeah, so I think I can stop here. Welcome for more questions.
Thank you. Let me ask one question. In the multi-agent RL, is there a way of incorporating some of the uncertainty quantification you presented in the first part of the talk?
Yes. So, for example, we have been working on like a different robust reinforcement learning, robust MARL algorithm. So, for example, if we don't specifically know the state information, we can design the algorithm by assuming. But if we have some uncertainty quantifications, and we utilize that part as state uncertainty, then practical algorithm-wise, we have something. Yeah. And also, I think learning this uncertainty for the transition function uncertainty that is more challenging than quantifying state uncertainty, but this is also something we have been working on recently. Yeah.
Thank you.
Yes. I had a question about the, you said the centralized training for all agents was expensive, but if you do like a subset, it is more efficient. I was just trying to visualize how the critic encoder would look like. Would it require like multiple forward passes? Is that what you're trading for?
Yeah. So this part is, also depends on your design for the communication protocol. So for example, we can set up the communication as only one hop, so only closest neighbors. Or you can also set up, say, communication depends on maybe communication range for the protocol you use, and perhaps in the range it's okay to do several hops of communication. Now, of course, you want to also consider, say, what can be the delays, etc. So actually, in the communication society, how to do this kind of mobile communication is not fully cleared yet. So there have been different methods like purely peer-to-peer communication. Also, vehicle actually first communicated to some road infrastructure, and then communicate back to other agents. So these are still topics that mobile computing and communication people have been working on. Yeah.